Welcome to Unit 2, Lesson 4. So you need to find the tasks to complete as usual. Please go to the Canvas Science2 page and look either under assignments or on the weekly calendar table on the first page for tasks for Unit 2, Lesson 4, U2L4. That's what we're going to be working through today. Goal today is to continue to explore projectile motion, this time adding in the idea of altitude, range, and drag. And then we're going to be sort of talking about how that can lead to orbit at the very end of things here. So before we get into that though, as usual, we'll do our little breakout room shares. The question today is, what's the best piece of advice you have ever been given? Now this could be like general life advice, or this could be like, you know, put a big keychain on your car keys so you don't lose them. It could be something small or simple. It's whatever comes to mind. I'll give you 20 seconds to think about it and then throw you into breakout rooms to share. Things are looking good. We worked on the Flipgrid in class. I'm seeing 13 responses. There are 14 people in the class, though. Again, some of you might have emailed it to me. So if you did, that's great. I will see that. But if you haven't posted that yet, make sure you have, though it looks like majority of you have done that. That was the water spin thing we did in class last time. Otherwise, it was the PhET simulation, which we also had class time to work on. It's looking like I've got that from most people. And then the reading reflection from Hewitt 5.9 through 5.11, which went into altitude, range, drag, that kind of stuff. Looking at the statistics on Canvas, looks like you're all feeling really good about those multiple choice questions. But was there anything you found difficult or confusing from those chapters or from that quiz? All right, we'll be reviewing it today too, using slides and doing a couple different activities. So next then is a, again, just remember to continue checking your grades tab. This midterm grades are being set this weekend. But otherwise, I put together an ed puzzle to further reflect on that last question in that PhET simulation about what is it about us humans and our evolution that made us so good at throwing. And so there's a short ed puzzle called How Throwing Made Us Human. It's about 4.5 minutes long. There are about 4 questions. I think they're open response though, not multiple choice. So I'm gonna time for 10 minutes to let you get through this. So this is step number 4 on the tasks to complete list. 10 minutes to work on that, and I'll keep an eye on the ed puzzle. I can see when everyone's done, and then we'll come back together to review it. So 10 minutes to work on How Throwing Made Us Human ed puzzle. Going to need verbal confirmation because I'm going to hide the tabs here so I can see what's going on. Is everyone seeing altitude, range, drag, and satellites?
Yeah.
Yes.
Yeah.
Alrighty, so I'll go through this quick because I'm assuming most of us feel pretty good. If anyone's a fan of Angry Birds, that game is entirely about projectile motion, right? And basically using a computer program to simulate it, and you're just trying to hit those little piggies or the structures that they're in. So in terms of angles, here's a really cool thing. Assuming you're firing from a level point, so let's say an elevation of 0 meters, and your projectiles are landing at that exact same elevation, then any angles that add up to 90 degrees, so for example, if you fired at 30 and 9 or 60, right? So 60 degrees and 30 degrees will land in the same spot, or 75 and 15 will land in the same spot, which I think is pretty nifty. But remember that this is assuming that there's no air drag, which is unrealistic because there almost always is, and that you're firing from the same elevation that the projectiles are landing at, right? And this makes sense if you think about it, because you can see it noted here that the speed with which a projectile rises will tend to match the speed with which it falls, right? Everything's sort of uniform. And so then if you can get angles to match each other in these uniform parabolas, you can find ways that they line up. But again, those are some pretty big assumptions that are being made for that rule. So obviously air resistance complicates things, and the specific way that it does that is it slows things down, right? So if you can think about altitude is always how high your projectile went, range is how far your projectile went. And so drag reduces both of these things, right? Because it's slowing down the overall path of the projectile. So in reality, projectiles never travel as far as we could mathematically calculate or expect them to go. And obviously this can change too, depending on the elevation, right? Elevation determines how thick or how thin the atmosphere is. So they hosted the Olympics once in New Mexico City, Mexico City, which is at very high elevation, and athletes were breaking records for throws and for jumps, chiefly because they're high performing people and they were in a much thinner atmosphere. And so you were actually seeing a little bit of an improvement with them. And likewise, if it's a windy day, it can really throw things off. I'm not the biggest baseball fan, but if you're ever curious about how do pitchers throw things like a curveball, which moves as it's going, it has to do with drag. Because if you get the ball to spin, as in this picture here, then that means that drag is unevenly distributed, right? You have a lot of drag towards the top of the ball and very little drag towards the bottom of it, which means the ball is actually going to move and curve a little bit as it flies. It has this sort of deflected wake. And so this is what professional baseball pitching is all about. It's just figuring out how to hold the ball and how to release it with a little bit of spin to make it do some unusual thing that makes it much harder to hit and also throw it fast. Speaking of fast, things get interesting when you start really launching at high speeds. So this is a little confusing, but what you need to think about is that if you were to drop a projectile for exactly 1 second anywhere on our planet, in 1 second it's going to fall 5 meters. So that's our sort of standard right there. This is just 1 second of fall over 5 meters. That's your vertical velocity, okay? Horizontal velocity depends on how hard you throw the projectile, right? That can change how far it travels away from you. And so here's sort of a funny situation. The curvature of the Earth, and I'm going to go ahead and assume that we're all in agreement that Earth is round. The curvature of Earth is that for every 8 kilometers or 8,000 meters of horizontal distance, there is a curvature downwards of about 5 meters, which is kind of convenient to think about if we think about it takes 1 second for a projectile to fall 5 meters. So that means what would happen if you launched a projectile at 8,000 meters per second? Here's a question, and I just need a yes or no answer. Would it hit the ground? Yes or no?
No.
No.
Very good, right? And that's what the reading is projecting. So yeah, it has fallen into essentially what we refer to as orbit, because it would just continue to fall around the planet. Now, again, I know that 8,000 meters per second doesn't sound that impressive, but it's actually pretty insane when you actually do the calculation into miles per hour. So hitting yourself in the back of the head with a ball is not something that's going to happen anytime soon, like in this picture, just because air drag would also slow down anything we threw inside the atmosphere. You have to get outside the atmosphere to actually have things truly in orbit falling around our planet. But this does kind of standardize things for us, right? So in terms of what we call satellites, which we learned in our solar system projects, are anything man-made or natural that orbits around a source of gravity. For Earth, the minimum tangential velocity that you need to get into orbit, and this is assuming that you're already outside the atmosphere, already in space, is 8 kilometers per second, which works out to be about 18,000 miles per hour, which is not anything you're ever going to try to achieve in a car on the ground. The air drag alone would destroy that, right? So you have to stay away from air drag. So this is, again, also why we as humans, right, if you want to launch a satellite, like a communication satellite, into orbit, it has to be outside the atmosphere. We have to get it at least 150 kilometers off the surface of the Earth, because at that point there's no more air, and so there's not going to be any drag acting on those objects, burning them up or slowing them down. So here's the key takeaway. Satellites orbiting at high altitudes are not under low gravity, right? Lose that concept. There's no such thing as zero gravity or lower gravity. They just have enough tangential velocity to continuously fall around planet Earth. And I have kind of a little simple short animation I want to show you quickly on my computer here, which I think emphasizes this well. It's an Edpuzzle I made, but so check this out. So you can see that it's launching at different tangential velocities, but once you get fast enough, it just goes all the way around continuously. And again, this is assuming there's no air drag, so you'd be outside of the atmosphere, but then it would just keep going around and around. That is orbit. And that is the key stuff from that part of chapter 5. Any questions or comments on that? All right. If we're feeling good, then we're going to do another little Flipgrid activity today, this time exploring your ability to throw things and the effect that drag has on it. So this is step number 6 on the tasks to complete. I've titled this How Far Can You Throw Flipgrid? As usual, the instructions are on the assignment as well as in the Flipgrid itself, along with the demonstration video. The gist of it is that you're going to be using a pair of socks. One sock is just completely loose and unfolded. The other sock, I want you to ball up, right? Fold it into itself into a firm, more circular shape. And you're going to be throwing those as hard as you can and counting with your feet how far they go. You're going to do that 3 times and enter the data into the quiz. So you'll notice this is actually a Canvas quiz, not just an assignment. And you'll have some questions to answer there as well. I'll time for 15 minutes to work through this. And let me know if you have questions or if you're not sure what to do. Please be safe. You're going to be throwing objects, so make sure you're in a clear space, that there's no glass statues or fire extinguishers or sprinklers or anything like that that you could potentially hit. Okay, 15 minutes to work on the Flipgrid. Let me know if you need help. Go for it.